In this lesson, we will be talking about solubility product. We will define solubility and sparingly soluble salts, refer to some grade 11 solubility rules as we go along, discuss a constant solubility product of KSP, predict the conditions for the precipitation of an ionic compound. We will solve some problems trying to determine the KSP. We will determine the molar solubility of a salt. We will predict precipitation when aqueous solutions are mixed. Predict the solubility of some sparingly soluble salts in ionic solutions. Those are some of the things we plan to do today. Some definitions here. By definition, solubility is a number of grams of the solute that can be dissolved in 100 milliliter of the solvent at a given temperature. The statement also implies that solubility changes with temperature. Solubility can be expressed using moles per liter or molarity. It can also be expressed as grams per liter or milligrams per liter or milligrams per 0.1 ml or 100 ml. Solubility here also implies that the solute could either be ionic or a molecular compound. Solvents could be liquids or solids. Sodium chloride is an ionic compound and has a solubility, but the solubility is reasonably high. Glucose is a molecular compound. It also has a relatively high solubility. Those are substances that we see disappear when you add it to a glass of water. Therefore, we say they are reasonably soluble at room temperature. Sparingly soluble salts. Normally, what we would have considered as insoluble ionic compounds in water, or the precipitate that forms in a double displacement reaction, will hereafter be referred to as a sparingly soluble salt. Sparingly soluble salts have low solubility. It also means even though the solid appears to be insoluble, there is a small degree of solubility for the ionic compound in water. The small degree of solubility can be measured by the change in conductivity of an aqueous solution, and that would be evidence for the solubility of the sparingly soluble salt in water or the precipitates that are present in an aqueous solution. What is a precipitate? In a saturated sugar solution, it is impossible to dissolve more sugar at the given temperature. The excess sugar that we add forms an insoluble precipitate at the bottom of the container, which may be referred to as a precipitate. So usually when precipitates are formed, the solution above it is saturated with respect to the substance. If you mix an aqueous solution of silver nitrate with sodium chloride, you usually get a precipitate of silver chloride. If the concentrations are right, definitely a precipitate will form. So concentrations do matter. Silver nitrate plus sodium chloride reversibly gives you silver chloride, an ionic compound with low solubility or a sparingly soluble salt, plus sodium nitrate. According to the solubility rules, all sodium salts are always soluble in water. All ionic compounds which contain nitrates as an anion, they are also soluble all the time. This is a rule that we had learned in grade 11. Silver chloride is the precipitate that is formed. It is a sparingly soluble salt. Formerly, it was referred to as a precipitate or an insoluble salt. We can safely say that the solution above the precipitate is saturated with respect to silver ions and chloride ions in aqueous solution. Formation of precipitates. A precipitate is formed if the solute forms a saturated solution in the solvent. For commonly soluble substances like NaCl or glucose, as we already stated, a precipitate forms when the solution becomes saturated and the quantity required is quite large because they are highly soluble salts. For a double displacement reaction, the precipitate is formed by the compound that has low solubility or only small quantity of the solute is required to make the solution saturated. So for the reaction between silver nitrate and sodium chloride producing silver chloride, which is a precipitate, along with sodium nitrate, which forms the spectator ions, in this reaction we can say silver chloride forms a saturated solution in water with just a small quantity of silver chloride. Or this compound has very low solubility. So compounds that precipitate, they have very low solubility, which means a small quantity of the salt can make a saturated solution. Molar solubility. The number of moles of the sparingly soluble solute or the precipitate that is dissolved at the given temperature to form a saturated solution, mostly in 1 liter. We can calculate molar solubility if you are given the equilibrium constant expression or the Ksp value. Now, one of the conditions for precipitation as we go along we will see is that if the ion product of a solution is greater than the solubility product, the solute will be able to form a precipitate. We will discuss that in a little bit more detail as we go along. Let's look at how we can write equilibrium constant expressions. So PbI2 is a compound with low solubility, which means it usually forms a precipitate when you mix two ionic compounds. PbI2 reversibly gives you Pb2 plus and 2I minus when dissolved in water. Even though I said dissolved in water, the solubility is very, very low. So using equilibrium expression rules that we learned in chemical equilibrium, we can write that the K value, in this case we're going to add the subscript Sp, referring to it as a sparingly soluble salt, is equals to Pb2 plus, which is an aqueous ion, into 2I minus the whole squared. And in the denominator we have the solid, which is taken as 1, so we don't write it. Similarly, if we take calcium phosphate, which is a sparingly soluble salt, produces 3Ca2 positive plus 2PO4 negative. So the Ksp expression is Ksp is equals to open brackets 3Ca2 positive close brackets raised to 3, which is a coefficient, into open brackets 2 phosphate 3 negative close brackets raised to 2, again the coefficient of phosphate. That would give us the equilibrium constant expression. There is a worksheet attached along with this. Download it and complete it so you can practice how to write equilibrium constant expressions or Ksp expressions. It's a requirement. Next, we will see how we can solve a problem, or we want to calculate the molar solubility from Ksp. The Ksp value is given to you and you have to calculate molar solubility. So the compound that I'm taking is lead iodide. Again, when dissolved in water, reversibly gives you Pb2 positive plus 2I minus. Ksp value is found to be 1.7 into 10 to the power of negative 5. Like we did earlier, the Ksp expression is equals to Pb2 positive into 2I minus the whole squared. This is the equilibrium expression. This is generated very similar to an ice table. So you wrote the equation PbI2, reversibly giving Pb2 positive plus 2I minus. Every time 1 mole of PbI2 undergoes dissociation, it produces 1 mole of Pb2 plus because the coefficient of PbI2 and Pb2 plus is the same. But at the same time, the concentration of iodide will be twice the value. Suppose we consider X moles of PbI2 is undergoing dissociation. It produces X moles of Pb2 positive, but the amount of iodide formed is 2X. So if you write the equilibrium constant expression, then we can replace the value with X. So this is what we see here. Ksp is equals to, we replace the value of Pb2 plus using the X value from here, and we replace the value of iodide or the 2X, and then we get Ksp is equals to 4X cubed. So if you rearrange the equation, you can solve for X, which is a third root of Ksp by 4. So this is the equation that you're going to use to determine the molar solubility or the value of X, or in simple terms, what we mean is, if you have a beaker filled with lead iodide as a residue at the bottom, and if the volume of the solution is 1 liter, the solution above is saturated with lead iodide, and the molar concentration of lead iodide in the saturated solution is what I refer to as the molar solubility. So the value of X will give us the number of moles of lead ions that are soluble in the saturated solution. So that's why we can calculate the molar solubility, or the number of moles of lead iodide that is soluble in 1 liter of the solution. So the calculation is very simple. I just replace the number of Ksp with 1.7 into 10 to the power of -5, which is a Ksp value. Don't have to memorize those values. They will be given to you. Solve for X. And in this case, the molar solubility is equal to 1.62 into 10 to the power of -2 moles per liter. So if you are given Ksp values, you can find out the value of X here, which is also equal to the value of X, which is the number of moles of lead iodide. In this case, the coefficient is 1 over here, and here it's 1. Therefore, that's what we're looking for. Let's look at the next problem. In this case, we are going to calculate Ksp from the molar solubility. So if you want Ksp, you actually need the molar concentration of the ions present in an aqueous solution which is saturated. So I'm just considering lead iodide again. So again, I have a beaker which contains an aqueous solution. At the bottom, I have lead iodide. Lead iodide is yellow in color. Let's make it yellow. So the solution above it is saturated with respect to lead ions and iodide ions. The molar solubility is given to you, which means I have actually given you the concentration of lead ions in this solution. So we have lead here in this aqueous solution, and I have given you the actual molar concentration, and this solution is saturated. That's what you have here. So I have a saturated solution, and I have given you the concentration of the saturated solution over here, 1.62 into 10 to the power of -2. So we are going to use that number, which is also represented over here with 1.62 into 10 to the power of -2, because 1 mole gives you 1 mole plus 2 moles. So once I have those values, all I need to do is substitute the value in the equilibrium constant expression for a sparingly soluble salt, which is this value. So Ksp is equals to Pb2 plus into 2I minus the whole squared. So I have to put the actual numerical value for Pb2 plus, which is over here. That's the value for X. That will replace the Pb2 plus, and 2I minus, this is the value that goes in here. So once you have those values, substitute it and you should be able to calculate. So we already have seen that I have replaced the value of Pb with x and 2i minus with 2x, and then I substituted with these numbers. So the final answer, 1.7 into 10 to the power of negative 5, is a KSP for lead iodide. This is just the opposite of the previous problem that we had done, and we got the same answer. So you get an idea of how to find molar solubility. That was the previous problem. And in this case, we are going to use molar solubility to find out the KSP. Bear in mind, every time we have an ionic compound that undergoes dissociation, it changes into ions, and write a balanced equation for that. The coefficients will tell you what the number of ions are. So if you know the molar concentration of lead in this case, you also know the molar concentration of iodide, which will be twice the value. So from KSP you can find that out, or from molar concentrations you can find KSP. That's a possibility, and that's an expectation. Now the only thing that happens is you can get confused with ideas with very specific words that have specific meanings. So make sure that you understand what's being asked by learning the meanings of these words. What does solubility product mean? What does molar solubility mean? One of the importance of this lesson is to determine the ability of a reaction to produce a precipitate when you bring into contact two reagents or aqueous solutions. So if I mix solution A and B, which contains ionic compounds, that would be a double displacement reaction that we'll be talking about. So if you mix the two sets of solutions of two ionic compounds that has the potential to form a precipitate, I should be able to predict whether a precipitate will form or not. And it all depends upon whether the solution that is formed is saturated or unsaturated with respect to the precipitate. And we can actually calculate that using what we refer to as ion product and solubility product. We had seen something similar in chemical equilibrium where we saw QC and KC. QC did not tell us, or QC did tell us that the system had not reached equilibrium if the value was different from the equilibrium constant. Similarly, we have a term here, we call it QSP, or we call it the ion product. QSP is the ion product, the actual concentration of the ions in the aqueous solution, and KSP is actually the equilibrium constant. This KSP, the sparingly soluble salt, the value of the product of the concentration for the given temperature, which value is going to remain a constant. So what we normally do is we calculate the value of QSP using the KSP expression, and then we compare the numerical value that you obtained with the KSP and make a prediction. The condition is if the ion product of the aqueous solution exceeds the solubility product, there will be a precipitate, which means the solution will be saturated with respect to the precipitate. If the ion product is dilute or is unsaturated, there will be no precipitate. So here we have a question for you. Can we expect a precipitate of lead 2 iodide, which is PbI2, to form when 20 milliliters of 0.0050 moles per liter of an aqueous solution of calcium iodide solution is added to 80 ml of 0.0010 mole per liter aqueous solution of lead 2 nitrate, which is PbNO3 twice. KSP for lead 2 iodide is 1.4 into 10 to the power of -8. So that's the problem. So that's the portion that you will be getting in a test or in a test environment, and you should be able to make a prediction when these two solutions, 20 ml and 80 ml, is mixed, whether a precipitate will be forming. So you will, as a matter of fact, write a chemical equation for this double displacement reaction, which means you're going to write the reaction CaI2 plus PbNO3 twice gives you PbI2 plus CaNO3 twice. PbI2 you have already seen is a compound with low solubility, 1.7 into 10 to the power of -5 was the -5 was the Ksp. 1.4 into 10 to the power of -8 in this case, as written here. So we're going to use those values to make a prediction. So bear in mind, this is a double displacement reaction. So in order to predict whether this reaction will take place or not, we are going to calculate the trial ion product. In order to do calculate the trial ion product, we will need the concentrations of the solutions. Once you mix the two solutions, you are given the concentrations of the ions before the reaction takes place. But once you mix the two solutions, the volume has changed, so it has a new concentration. So the two solutions that are given are calcium iodide and lead nitrate. You already know that if you take 1 mole of calcium iodide, it dissociates to give you calcium 2 positive and 2 I minus. So every time you take 1 mole of calcium iodide, it produces 1 mole of calcium ions and 2 moles of iodide ions. And that is something that you should have in mind right away. Now, if you take 1 mole of lead nitrate, PbNO3 twice. So if you look at this, PbNO3, it produces 1 mole of Pb2 plus and 2 moles of nitrate. Now in this case, we are interested in the concentration of lead ions and iodide ions. So that's what we'll be looking for. The calcium nitrate that is formed, they form spectator ions. They do not precipitate. And therefore, I'm going to write the net ionic equation for this reaction. So the expectation is when we are doing this lesson, you know what is total ionic equation and net ionic equation. So the equation that I have written here, this is the net ionic equation for the reaction between calcium iodide and lead nitrate. So when calcium iodide and lead nitrate react, this is the net ionic equation. It produces the precipitate, and that's what we see here. So the expression for QSP, which is the same as that for KSP, is equals to QSP is equals to Pb2 positive into 2I minus the whole squared. Now we will have to determine the molar concentrations of lead ions and iodide ions when you mix the two solutions together. That's what we're going to do next. When I mix 20 ml of a solution with 80 ml, the total volume of the solution becomes 100 ml, which means the reagent that I have taken in 20 ml is going to be diluted. The equation for finding the concentration of a new solution is the CI/VI is equal to CF/VF. CI is the initial concentration, VI is the initial volume, CF is the final concentration, and VF is the final volume. So we know the final volume is 100 ml, initial concentration is known, we want to find out CF. That is what we need to do. So taking this information, we will see how we can do that. Mind you, we are looking at the concentration in this new volume, which is 100 ml, and that's why it's dilution. So 20 ml CaI2 plus 80 ml PbNO3 twice is 100 ml. Ci for I minus. I minus comes from calcium iodide. CaI2 dissociates to give you Ca2 plus 2I minus. So the concentration of iodide ions, so this is iodide, is 2 times 0.005. 0.005 molar or moles per liter is the concentration of calcium iodide. Every time you take 1 mole of calcium iodide, it produces 2 moles of iodide ions when dissolved in water. So the concentration of iodide ions is actually 0.01 mole per liter. Okay, so now we have the actual concentration of iodide ions when calcium iodide dissolves in water. So the initial concentration will be taken as 0.01. So this value is what we're going to look at, 0.01. And the volume, we are going to change the volume to again liters. 20 milliliters is changed to liters. So CIVI is equal to CFVF. So CIVI, VI, the initial volume is going to be 0.02 and the final volume is going to be 0.10. 100 ml is 0.1 liters. So we're going to use those values and solve the value for the concentration of iodide, and the final value will be 0.002 moles per liter. So this is the concentration of the iodide ions in the solution. On this slide, we will determine the concentration of lead ions. So the initial concentration of lead ions is 0.001. We already know when lead nitrate is dissolved in water, it produces 1 mole of lead ions for every mole of lead nitrate. Therefore, we don't have to multiply it by any number. It's just the same concentration. So again, we're going to use the same equation. CIVI is equal to CFVF. And the initial concentration is, again, we have it here, is 0.001. The initial volume is 0.080 liters. That's the volume in liters. And the total volume is 0.01 liters. So using this information, when you calculate it, the concentration of lead ions will be 0.0008 moles per liter. So now you have calculated the concentration of iodide ions separately in the previous slide and the concentration of lead ions in this slide. Here we can substitute the values of lead ions and iodide ions and then calculate the value of QSP. Substituting the numbers, for lead we just calculated in the previous slide 0.0008 moles per liter, and for the iodide you have 0.002 moles per liter. So we have those two values, and it is also raised to 2. Solving that will give you QSP is equal to 3 into 10 to the power of -9. And KSP is already given as 1.4 into 10 to the power of -8. Since QSP is less than KSP, it doesn't satisfy the condition that ion product should be greater than solubility product for a precipitation to occur. If QSP is less than KSP, we have an unsaturated solution of lead iodide and we will get no precipitate. That's what this means. Every time the value of QSP is greater than KSP, the solution will be saturated. So that's how we solve a problem predicting precipitation. This is the third type of problem that we have seen today. Here we have a slightly different problem, which is similar to a Le Chatelier's principle problem. The question is, the solubility product of AgCl in water is 1.5 into 10 to the power of -5. Calculates its solubility in 0.01 mole per liter. So what you really have is you have a beaker which contains 0.01 molar NaCl, and into that you are adding AgCl. That's what you have. So adding an insoluble or sparingly soluble salt into 0.01 mole per liter of sodium chloride. And sodium chloride is actually a very strong electrolyte. Therefore, if you dissolve it in water, it breaks up into sodium ions and chloride ions. The concentration of sodium chloride is also equal to the concentration of sodium ions and chloride ions. Therefore, we have the concentration of sodium chloride. We have the concentration of chloride ions. Now, when you put silver chloride into it, AgCl will undergo an equilibrium shift, gives you Ag positive plus Cl minus. So this is what you have, a reversible reaction. And if you increase the concentration of the chloride ions, what happens? Equilibrium shifts left. That's what really happens. So when you add sodium chloride into it, you're adding the chloride ions. So bear that in mind while you're solving this problem. And we want to calculate what is the new molar concentration of silver chloride in sodium chloride. The solubility product of silver chloride in 0.01 mole per liter sodium chloride is X moles per liter. So we are assigning a value for the solubility of silver chloride to be X. Then from AgCl that is dissolved, we can write this equation. AgCl reversibly gives you Ag positive plus Cl minus, or Ag positive is equals to Cl minus because the coefficients are 1 and 1 for both of these. Therefore, they both have the same value of X. That's what we have here. Now, if you look at the concentration of chloride ions, that's found to be, it should be 0.01 moles per liter from sodium chloride plus the chloride ions that are formed by the dissociation of silver chloride over here. So this is what we see here, the dissociation of silver chloride, giving you some chloride ions. So the total amount of chloride ions in the solution will be 0.01 plus X. Now you know that the value of Ksp for silver chloride is 1.8 into 10 to the power of negative 10. The value is extremely small, which means the value of X is also extremely small. So if you find out the percentage of X in 0.01 times 100, that value is going to be extremely small. So what we're going to do is we're going to make an assumption that the concentration of chloride ions is equal to the concentration of NaCl, which has a higher concentration. Once you make that assumption, write an equilibrium constant expression, substitute the values, and you should be able to find out the molar solubility of AgCl in 0.01 mole per liter of Ksp. Expression is written here, and that's this one. Ksp value is given, it's 1.5 into 10 to the power of negative 10. We want to find out how many moles of silver is present in it, which also means that is equal to the number of moles of silver chloride because the ratio is 1 to 1. Now solving for X, excuse me. Now solving for X, you can get value of X is equal to 1.5 into 10 to the power of negative 8 m, or the solubility of silver chloride in 0.01 mole per liter of sodium chloride is 1.5 into 10 to the power of negative 8 m, or moles per liter. So this is the fourth type of problem that you have seen. Now there could be variations of these problems where we can ask you to find out the concentration of either the positive ions only or the negative ions, or we can ask you what may be the number of grams of the precipitate that is formed, because we know the Ksp value and the concentration of the ions in the saturated solution. Anything more than the concentration of the saturated solution will precipitate, so we can calculate those quantities too. That's it for now. Make sure you download the worksheets that are posted in Google Classroom, answer them and submit them. That's it for now. Thank you and have a great day.